Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we are going to discuss the performance of demand paging. We will calculate the effective access time of some process to see that how demand paging is improved and how it is concerned with the memory performance of a system. And what are the advantages of the performance of demand paging and what needed to be done to the demand paging to get into that level of performance improving. Demand paging can simply affect the performance of a computer memory system. So we will calculate the effective access time to see that how it is done. First we know that if no pages are in memory, then all pages will do page fault. And if all the pages are residing in the memory, then no page fault will occur. Then the effective access time will be equal to the memory access time. The memory access time is the time that the page is in the memory and it is then reading in the page only from that memory. Generally, it varies from 1 to 200 nanoseconds. Now, if the process or page is in the memory, as we say that effective access time will be equal to the memory access time. But if there is a page fault, then it will be considered and the effective access time will be changed first to make the desired page brought into the memory and then process or access that page. So thus the effective access time can be calculated as So if P the probability of a page fault and that lies between 0 to 1, that is 0 less than equals to P less than equals to 1, and this P it tends to be more close to 0, this only requires or wanted by that some page fault or a fewer page fault is needed. So now to calculate the effective access time, as we can see that 1 minus P, that the processors that are already in the memory will be given a memory access time and the processors that are page faulted will be needed to multiply it with the page fault time. Now if a page fault occurs, then to calculate the effective memory access time, the page fault time needed to be considered. Now the page fault time can be calculated with the following sequence. First, when a page fault occurs, we need to trap it to the operating system. Second, we need to save the register, process state and instruction register or contents. Third, we need to determine that the interrupt was a particularly page fault. Fourth, we must decide that the page where it is indicating and defining the location or address where the page is residing on the disk. Fifth one is we used to issue a read disk from this page or disk into the memory. And to do that, first we need to waiting for the device queue to get actually the interrupt request received. Next, to wait for the device to actually have the latency time or the I/O completion. Third, we start the processor translation of the disk to the memory page. Next, we have devised it, and next we have brought into the page into the memory. We should wait for the CPU to allocate to other processes while we are waiting for the I/O. Now we should receive an instruction or interruption for the disk I/O that the I/O is completed. Next, we again save the register set or the instruction register, content and process state if other processes were allocated the CPU. Next, we will now update the page table and the tables internal kept with the process that the predefined desired page is now in the memory. Next, we should wait for the CPU to again allocate the process. And at last, we should restart the execution depending and loading the page table, the new process state, saved content registers and instruction registers into the memory. Now this much time it will require to solve this page fault time. So this page fault time will require a large amount of period if there are more pages that are residing on the disk and that need to be in the memory. Now, not all the steps that are required to process in every necessary process page fault. In some of the steps, like while we are waiting for the CPU utilization or waiting for the I/O, the CPU is allocated to other process to maximize the CPU utilization in some multi-programming environment. But it also increases the effective access time and also increases the swap time to restart the process execution when the disk I/O is completed. Now, in every case, there are three major components or problems that are faced with the demand paging. Number one is the time for servicing the particular interrupt. Next one is the reading for the page, and the third one is the restart of the process. Now, the first and the third problem can be solved with extra careful of coding to hundreds of instructions per second. As we can know that the effective access time varies from 10 to 100 microseconds, and the page fault time in that case can vary from 8 milliseconds and near about, where it takes a latency period of 3 milliseconds, a seek time of 5 milliseconds, and a transfer time of around 0.05 milliseconds. So it will cost around 8 milliseconds of this page fault time. Here we are concerning with only the device service time, that the device needed to be serviced the request of writing in the page into the memory. But we have to always add the device queuing time if there is no paging device available, and we need to wait in queue for the paging device to be available before a request can be served. Thus, more swap time will be increased with the swap time or page fault time it is already have. So now if we have a memory access time of 200 nanoseconds, then we can calculate an average access time with the page fault rate of P probability and having a page fault time of 8 milliseconds. So from here we can see that the page fault rate is directly proportional with the page fault time. The either probability of the page fault increases, so the page fault time will also increase. Now from here we can see that the page fault rate will be decreased if we have one access between the 1000 access, that is a page fault. So now it will become only 40% slower. That is also a huge amount considering when we are talking about the time demand paging. Now to increase and the effective access time decreasing, so 10% of this demand paging time or the page fault time to be considered. So see that how page fault will be lesser. So here we can see that the page fault should be at least a fewer than a complete instruction for every 3,99,000 instructions, so that we can acquire a 10% slower rate along with this 8.2 millisecond, that is a 40% slower rate. So when we are talking about demand paging, we should consider a very low page fault rate to actually acquire the advantages provided by these schemes. Otherwise, the translation of this P will definitely occur and the system will go dramatically slow and ultimately it will crash down. So for demand paging, another aspect is for all of the use and handling of the disk I/O swap space. We know that the disk I/O swap space is faster than the swapping from the file, as because the disk I/O is having larger memory chunks that of the files. So when we need to copy the entire file image into the swap space, and then generally paging is done from that swap space only. All file lookups and indirect allocations are not done here, so only demand paging is done from the swap space and not from the file. Another option available to solve this problem is to first initially replace the pages from the file system to the main memory only. But once the page is replaced, it is written to the swap space so that the next time the page is referenced, it is found in the swap space only to increase the performance of the demand paging, and thus overall increasing the system's improvement. Now, if we can recover from this swap space of directly using the file system as a backing store, then we need not to store any of the file images in the file system or the backing store. This can be improved and we can remove the page fault rate for the using demand paging binary files. At this type of files, the overwritten of the file can be done at each page replacement policy. When the pages are replaced, they are simply overwritten and can be restarted again with the instructions, so that the file can be swapped entirely from the file system, and the swapping space is only required when the anonymous requirement memory, that is the disk I/O that is not associated with the particular file, is not presented there. The method approaches good and is implemented in many operating system in Windows, Unix and the free version of the BSD. Now if we talk about the mobile operating system, it does not support any kind of swapping. It directly demand pages the disk operation from the file system and the read-only code for the file system if they are needed later. However, it generally not reclaim any of the anonymous memory until and unless the process which is using that anonymous memory, it terminates or explicitly pass over the control to the operating system itself. So in this way, effective memory access time can help in reducing and increasing the performance of the demand paging to be used as an advancement of a virtual memory management scheme. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.